All right. So the directions say to change things to sine and cosine, and normally that's a good idea, but tangents and secants kind of go together too. We have a Pythagorean identity with tangents and secants in them, so I'm going to leave them be for now. Um, and so the other tool in my toolbox is if you ever have separate fractions, you probably want to combine them, common denominators, right? So if I were to get a common denominator, it would have to be the full secant theta minus 1 times secant theta plus 1. And in order to get that, I would need to multiply this first guy by what it's missing, top and bottom, so that it's a fancy form of 1, right? And then same thing for this guy. He needs the secant theta minus 1, top and bottom, fancy form of 1. So we're multiplying by 1. We're not changing anything. We're doing no harm. And so the denominators are now the same, so we can add the numerators. So I'm just going to rewrite what I have so I don't mess anything up and distribute after. There we go. And yeah, so now I'm set. I'm going to go ahead and distribute here and here and here and here. So I get tangent theta secant theta plus tangent theta plus tangent theta secant theta minus tangent theta all over. I'll rewrite the denominator as is. Excellent. And we are quite happy with this because we notice we have tangent theta minus tangent theta, so that just goes away. And then I have like terms, tangent theta secant theta plus another tangent secant theta. I have two tangent theta secant thetas. So I have two tangent theta secant thetas on top. And the bottom, if I keep it as is, nothing's going to cancel. And I wouldn't be sure what to do. So even though I normally like a factored form, I feel like it's supposed to simplify further. So I'm going to go ahead and FOIL out the bottom, see what happens. So I'm going to get secant squared theta for that guy, and then plus a secant theta, and then minus a secant theta, and then minus 1. And I'm pretty happy with that because the secant thetas cancel, and that secant squared theta minus 1 is that identity that we were talking about. So if you don't know that one, you know your Pythagorean theorem identity, and you know if you divide every piece by, I want secant, so I'm going to want to divide by cosine squared. So if I divide every piece by cosine squared, we get 1 plus tangent squared equals secant squared. And so it's 1 tan secretary. And then I notice here I've got secant squared minus 1, so if I just toss that over, tangent squared theta equals secant squared theta minus 1. So that bottom is just tangent squared. So I'm going to leave the top the same, and I'm going to make the bottom be tangent squared. And then even more brilliance, one of those tangents will cancel. So we have 2 secant theta over tangent theta. And then now I will change everything into sines and cosines because I suspect more will happen. So secant theta is 1 over cosine theta, and tangent theta is sine theta over cosine theta. Bunches of ways to figure out cleaning up that fraction. Some of you can see that that cosine on the bottom of each is just going to cancel, and so that you're going to get 2 over sine theta, which is just 2 cosecant theta. If that's too scary for you, you can do old school. If you are dividing fractions, if you wrote that as, hey, I'm dividing by sine theta over cosine theta, then that means I'm multiplying by the reciprocal. So keep, change, flip, and then the cosines cancel. But it's kind of a funny, like this is how we learned it in elementary school, so it's kind of comforting to go back to it. But that keep, change, flip, it's like, well, why does that work? And the whole reason it works is because you're multiplying by this fancy form of 1, cosine over cosine, so that, which I suppose you could write as cosine over 1 over cosine over 1. So now if it's more convincing to you that those cosines cancel, that's why we're getting that. Ah, so beautiful.